has to, so it's a chain of reasoning, chain of deductions, and you can't put false stuff there. You can put contradictions there, but not so. Since both are this, when we negate this, we are saying, hey, I know that the negation is true, and this obviously we have assumed to be true. So we can start adding this. All right. So there's that business. So I added a note here where, last time we're going to start here. And so start here, proof, keep going down, then bring P in P, or you can begin with either. But you have to use both to get a contradiction. Okay. And then I added this. And then this is the old stuff here. And then you should look at all of this. And here what I did is I copy pasted from the textbook Haggerty how it looks like in the textbook. So you want to look at this and go, can I comment? Can I figure out what's going on here? And what I do is I go through this thing right here. And let's see, what do I do? Then I do this with all the commentary. Okay. So I add all this stuff, trying to make sense of what's going on, and also trying to make sense that you know what the steps and all of that. If there's something complicated, I add extra stuff here. So in the textbook, all you had was this block. Okay. And then I do this, and this is perhaps from computer science background where I would write code, and then you're supposed to have commentary, comments on the side. And this is a good practice because you don't want to go back to this. You want to go back to this. And if you don't have this, you won't remember what's going on. So once you figure that out, so one of the things, if you really get into this and you don't have to, is look at this, go through this, come back to this, write out these lines and say what kind of commentary you can put. And you can cheat and steal and all of that. Okay. And so I did the same thing for the indirect proof and for the last one. So in the book, it looks like that. And in our PowerPoint, it looks like one line, second line, third line, fourth line, fifth line with comments on the right-hand side. What I did is for the proof by contradiction, I added my own line here saying that, hey, we need to start with the consequent or the conclusion, the negation of. And then, but it doesn't really matter if you put that there or not, it still works. Okay, all right. So what I want you guys to do is go ahead, read this. Not a good idea. Read this, and then I'm going to do this on the blackboard, okay? While I take attendance. Assume that N is and so I'm changing it from the slide, is a natural number. Just to shorten it a little bit. Okay, so this is one of the assumptions that he just sticks in there, unfortunately, right? And then he says, what he really wants a proof of is this thing here. If n squared odd, and that's how he has it in the textbook, then n is odd. Okay, so you stop and you go, all right, the number n is going to be a natural number, which means it can be 1, 2, 3, 4. And if any n that you choose, let's say it's 1 or 2, okay, let's do 2 and 3. If you choose 3 and square it, okay, if you choose any natural number and you square it and it's odd, then it cannot be 2 because 2 times 2 is 4. It better be one of the odd ends. 3 times 3 is 9, okay? So therefore, one can deduce from the fact that this n better be odd for this to be true. And then it says, this implies that the n that was here that made this true, the n that was here that made this thing true better be an odd n. Yes? Okay, all right. Okay, before we go on, what do we need in this? We need the idea of, so what is something that we'll bring into? We're bringing a lot of understanding of mathematics already. And one of them is that any positive, and this is a positive whole number or a natural number, can be expressed as a product of prime factors. Any number you take can be that equals a product multiplication of prime numbers. So that's something we'll be bringing in. And that is not here, but it is part of the knowledge of mathematics that we can bring in, okay? All right, so what's the first step? We write proof. And then I'll just go ahead and do this and pretend that this part was also inside here. But you don't want that because there's an issue. So I put that in first. It works for the direct proof, but then it doesn't work for the other ones. So anyways, what is this thing called? Antecedent. So basically this, very good. And who was that? Very good. And I need to get down the name. So Alexa is right. Or hypotheses. Trying to say that correctly at home. This one. Hypothesis. Is that how it's said? Hypothesis? The Greeks are, I should never learn Greek. Okay. Of course, antecedent is a nice Latin word. And then Alexa, N is odd would be consequent, or the easy one, conclusion, consequent. Both of these are Latin words. All right, so proof. What should I do? Where should I start? What can I assume true and use that as a true statement of fact and stick it right here?
Every number two factors.
Okay, or that we could take one of the assumptions, right? We could start with this, right? This is pretty good, but we don't. Okay, okay, let's go rewind back. We're going to start with the hypotheses and antecedent, and the way I've underlined this whole thing is antecedent. And so we should logically, usually in a proof, we would start right here, okay? So, and it's going to be different from the PowerPoint. So I'm going to go ahead, ignore this line and start right here. So I'm going to write, my first step is n squared is odd. I just put an is there. Okay, so it's slightly different. It's quite a bit different, or maybe not that different from the PowerPoint. So you want to take notes, maybe. Now, so let's do comment. And I'm going to do, what should I write here? What did I just do? I took the antecedent and stuck there, assuming it was true. So I should write, assume the antecedent to be true and write it out as my first step. Okay, and now what we do, we want to deduce from this, right? We want to take it somewhere. And we want this to look like that. This is our destiny. How do we make this go there while this whole odd business is still true. So what can I do here? Expand, very good. So we're going to expand this. We're going to take the n in n squared, and this could be a mistake. I should have just followed my PowerPoint. So if I screw up, it's your fault because you didn't stop me. N, always blame other people for your mistakes. N in n squared, we expanding, let's see, expanding n in n squared. Alexa's an English major. Solid. Okay. So we expand it into, what was that last time? I'll put some notes here. 12 equals 2 times 2 times 3. Each one of these are prime numbers. So, but this is any n, not a specific n like 12. So we need to bring in the level of generalization. So P1 stands for some prime number, P2 stands for another prime number. Both of them are being multiplied and they equal n. Is that correct? And if you remember, this is almost there. Why is it incorrect? Because I have 3 here. I just put 2 here. How many prime factors should I put that if multiplied together will get me this n here? So it's quite different from the PowerPoint. Cheating, you could look up the, yes, Jada. Okay, very good. Go on forever. And in fact, the textbook go all the way to the kth prime number. Kth could be 3. Again, keeping with the generalization. I could have put 3, but I don't know what n is going to be. N could be anything. If it's n is 100, 3 is not going to work. K would be a bigger number then. All right. And then at this stage this is going really well. And now we need to take this thing here and start to make it look like that so that we finally, right? Because you want to start with, yeah, maybe I shouldn't do it like that. All right. So what am I doing wrong? In the PowerPoint, we start with, as Russell said, n is a whole positive number. And then we expand n like that. I'm just trying to do this and see if it works. So the next step is, I should not have done this, that, okay, so let's just make it like that. So n squared equals, so what have I done? I've just used the rules of quotients and product, rules of exponent, the rules of exponents, which tells us that you can bring 2, the exponent here, the power, and multiply each of these factors. And this thing is equal to that. Okay. And at this stage, we are saying this whole thing. Why is this still true? Why still true? If this is assumed to be true, then this thing is what? What's the difference? Is this different from, is this line, why is this the same as this? Well, both are odd, but also just this bit here. This is basically the same as this. Yes. Okay, so this thing is definitely equal to this. And then this is definitely equal to this, where all we've done is we've shown that n squared equals the square of the product of prime numbers using, so we could do that expanding, and I need to write one other thing here. Let me write it here. So for this step we did applying, so this is what we did here, applying prime factorization. Sorry about that. So that's what happened here. We applying prime factorization to the last step, we get this. Then applying the rule of exponents, we're able to bring the 2's in. N squared is identical to n squared equals the product of primes squared, because all we've done is expanded that. These two things are same, and then we get this here, right there. All right, when is this not true? Or when is this not a prime number? When is this product not an even number?
2 is not.
When 2 is not one of these. When 2 is not it can, every other prime number will work, but if we have 2, then what happens is, if I did this, I should have stuck with my PowerPoint here. If p squared equals 4, if p1 equals 2, we get a 4, which is the same thing as 2 times 2, this whole thing. And is this an even number? Yes, it is. So none of these can be prime if this is going to stay true. And that's what this weird little proof does. So we write, because of this fact, that if any one of them, P1, P2, P3, or PK, one of them is a 2, which is also a prime number, but it's an even prime. How many even prime numbers are there? 1. Which one is it? 2. Every other prime number is odd. Is that true? Yeah, okay. All prime numbers are odd except for the first prime number, 2. 1 is not a prime number, it's a composite number. Okay, so at this point, we can say, so we're going to deduce a statement of fact from here. In order for this line to be true, in order for, let's say, step 1, step 2, and step 3, in order for step 3 to be true, none of the P's. So now we're saying we're using this I here to represent any of these numbers. Okay, so none of these PI's can equal the prime 2. Since none of these primes can be equal to 2, then even if if that is the case, then the n is odd. Can you see that in the fact? And this is what is sticking here. This seems not very satisfactory because I did this. But please look at the PowerPoint. And you take the notes here. I'm going to redo this the way it's in the PowerPoint just for the hell of it. Okay? like what Russell was telling me to do. And reason why the textbook is clearer is that there's no square there messing around a little bit. Actually, the square does come in. I think this is fine. Yes.
Are we gonna continue finishing with this example though, or are we like moving on to that?
So yeah, actually, I'm not. Yeah, I'm done with this. Unfortunately, we'll do bunch of. Well, we'll do one more direct proof in the class, and then every other proof will be proof by contradiction. Yes.
But just for like notes,
Hmm.
that's not considered complete, or is it? Like,
Oh, right. Oh, that's your question. Sorry. So I could write then n is odd is true. And then what you do to complete the proof is you put a box here. And box is what tells you that the proof is done. So this square box, or so it's just this box here. Or people used to write QED. Why did the proof end here? Because we got to the antecedent. I want a consequent, which is right there. We started with the hypothesis, the antecedent. We messed around, then we made a statement of fact about step 3, and that told us that none of the p's are 2, therefore n is also is odd. Okay, it's actually pretty close to what it is in the textbook. And to show to your professor that the proof is done, you put a square. This is called Halmos. This is a famous mathematician who started putting squares rather than QED, which is Latin for God knows what, but the proof has ended. Okay, let's move on. Let's if this is true, so usually what happens is for a lot of the theorems, doing a direct proof is not possible. And the two methods of indirect, the contrapositive and the proof by contradiction usually works. But, or it's easier. It's easier to show this with the proof of contradiction than this. Okay, let's do the second method. So we've got the same proof. And what we find, apparently, which is not true in this case, is that this apparently to us is a richer place to start. This is what we can really work with, and we wanted this to be in the antecedent. And we think that we can deduce from this thing. So we want to put this as the conclusion, this as the antecedent or hypothesis that we will assume to be true. So, all right, so we have to rewrite. And let me get my cheat sheet here. Here we go. So, nothing's changed. What's the first step? We want to express what we want to prove, change the form of this to its contrapositive form so that the conclusion comes first and the hypothesis or antecedent comes second. So first thing I'll write is assume that the negation. Oh no, sorry. Rewrite the implication, which is that if and then thing, as if, and notice if you're taking notes, leave some space here, n is odd, then n squared is odd. Okay. Is that correct? Well, what's the mistake here? Contra positive. Contra is against the positive. So Alexa knows, yes, I should add a not here. Very good. And now this hypothesis, this implication is identical to this implication, according to the truth table. Okay, since we don't have space, I'm going to move this here. So first line, first step of our, let's see, proof. Step one. So is if not n is odd, then not n squared is odd. Okay. And let's see what the book did, because this seems very cumbersome. So what's the opposite of not? Not n is odd. If n is not odd, it is going to be even. So I'm going to replace this with n is even. And then not is applied, this operator not is applied to n squared is odd. The opposite of that would be n squared is even. So I'm going to put that there. And now we're ready to go. This is the negation of the conclusion or consequent. And I have put it where the antecedent usually goes. This here is the negation of the antecedent, and I've put it here as the conclusion. And my reasoning is that for some reason, I think that I can deduce that this statement is easy. With this statement, it will be easier to go from here and get there rather than the other way around. In fact, we just saw it doesn't matter what the order is, okay? All right, so what's the first step? So this is the first step where we rewrite. So we just rewrote the original as its contrapositive. Okay, so where should I start? With the antecedent, right? Very good. So the first step is I'm going to say, assume n is even. I started right here. And last time, what did we do with n? We used the idea of prime factorization, right? And this time, rather than use the idea of prime factorization, we're going to bring another idea of, we want to expand from this statement. It says n is even. When is n even? When is n odd? It turned out if we took the prime factorization of n when it is odd, there will be no 2 in that prime factorization, right? N is even, we can't use that idea. So what we do is we use another, the definition of, question? No, definition of the form of even number. If n is any even number, so I'm going to actually write applying, we're going to apply this. We're going to expand n and give it the form. N is only going to be an even number if it has 2 in it. And then k equals 1, 2, all the way to infinity. So if I put 1 here, so this is k equals 1, 2, 3, 4 forever. If I put 1 here, I get 2. If I put 2, I get 4. If I put 3 in place of k, I get 6. So I always get even numbers. So this is the form of even numbers. So just like before, when we replaced n with n equals p1, p2, dot, 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 pk, we're going to take this and replace it with this form. And rather than using the letter k, the textbook uses the letter m. So this statement here can be written as n equals 2m. So this is step 2. Step 3. And what happened in step 3? We are applying the form, applying this to n, assuming n is an even number. So now by step 3, we have this thing going for us. And where do we want to go? We want to go to n squared is even. So what's the next step? We could just square it, right? All right, so we're going to do squaring this thing here. If I square it, I get n2 4m squared. Okay, so we've assumed n is even. And what we're really doing is we're just doing a direct proof. We're not worrying about the negation at all. Well, rather than working with odd numbers, we are working with even numbers. And what I'm just doing right now is what I just did before, but it's much nicer to do. And I'm not really messing it up at all. So if n squared is going to be an even number, there better be a 2 as a factor on the right-hand side, right? So what do? I just rewrite it again. N squared equals 2. And does this not look like 2k? And so we can say that is this equivalent to this? Why is this equal to this? Because I can take the square root of this. If I took the square root of both sides, the left-hand side and right-hand side, I'm going to get this. The square root takes out, cancels the squares. This becomes 2 and this becomes, let me just do that. If I did n squared, square root, and there are all bunch of laws here, but so this cancels, you get n, and then this becomes 2 and this becomes m, which is exactly that. So when you square something and you get this, you can always go back to that if you do the opposite of what you just did. If you took a square, you take the square root to get back to the original one. Therefore, these two things are identical. So, okay, so at this stage, what do? We want to come to n squared is even. So we say that this whole thing, we can just make that statement is another even number because it looks like 2k, and therefore this n, if you square an even number with another even number, can you get an odd number? No, okay. And the fact is that you've been told that this is even. If this is even, then it's, okay, so this number is even, and it is equal to a square of n, and n can only be even if n is even to start with, which is what our assumption was. The assumption hasn't changed. Because the assumption is that n is even, the square of even number should get you an even number, and we just showed that over here. So it's kind of like it's such a simple proof that it's kind of confusing, but since we assumed n is even, the square of the even number better be even. And we prove that it is even because what is on the right-hand side looks like 2k. It has a factor of 2 in it. Okay? Ask me, what the hell am I saying here? Confusions, folks. Before I finish up, I just need one more line. James? Yes? Say it again? Oh, shit, no, go do more than that. Okay, so tell me what I'm saying here. What am I saying here? Our assumption is n is even. If we square an even number, according to the folklore, we're going to get an even number again. So that's another law. If you multiply an even number with another even number, you get an even number. Another folklore law is if you multiply two odd numbers, you always get another odd number. Here we have n squared. If we multiplied it, this is the number I'm saying you're going to get. And is this number even? Yes, because it looks like 2k. Okay, so why did we expand that? Because when we square it, we get something here, and that better be even. Okay, this is n squared is even, and so is n. And so if n squared is even, that means the original n was also, so therefore n is even. And I don't know if you guys can see it in the back. N is even is n squared is even, which is where we wanted to go. Why? So why can I use the word therefore? Because I am showing here that if you square an even number, you get an even number because the form of this thing in this box looks like 2k. And what do I do now? I just put a box here that I had from previous. And I just put a box right here at the end to say I'm done. Okay. We have 4 minutes. All right, so I'm going to stop here and let's quickly look at the exam. Okay, and then on Wednesday, I'll go over the proof by contradiction. And please, again, look at the PowerPoint, look at your notes, and get the hang of this. We will be doing a lot of proofs, so hopefully. And so this will make more sense as we go along. So I should do this. And then pull up. Where? Okay. All right, so I have to go to. So this is a new exam, so I might be revising it a little bit. So sorry about that, because I did not, nope, not these. Oh yeah, these. No, I'm in the wrong place. Sorry. I did not use this exam last semester. So this is brand new. So I might be trying to fix it. Okay. All right. So here we go. So I give you some background, and I say that a metaphor in poetry is used to compare two distinct things that share a common quality or characteristic. And we use the metaphor by stating that one thing is the other, even though they're not literally the same. So the silken tent in our poem is like the she of the poem because they share a quality or characteristic. In fact, they share a bunch of characteristics and qualities. And that's why they can be compared. Okay, so, and what I wanted to do was, so as I said, I'm going to make changes here. Sorry about this. If I should, Well, okay, I'm gonna keep it right. I'm gonna, because we don't have time. Okay, we got 1 minute. Let's see. Let's see. In other words, two distinct different things like a silken tent or a she are compared to each other if, and they better share a set of attributes or characteristics underlying the superficial surface difference between these two entirely different things. A tent does not look like a woman or a she, but it turns out they are similar. So the principal qualities of the she starting at line 7 all the way to the last line are, so I need to do this in reverse. So I just started with that. So I'm gonna fix that. I found sureness of soul, ties of love, loosely bound, and then I've added something almost without turning into bondage. So if you look at the poem, line 7 is right here. And I started putting, I took this, I took the sureness of the soul, ties of love, and the bondage business. And I said, these are the main qualities. So I just picked these up. And then, while the principal qualities of the silken tent are at the beginning of the poem, and those are ropes, relent, and I equated that with ties of love. Poise at ease, I thought was identical to loosely bound. And then sureness of soul, I thought pinnacle to heavenward. Okay, so what am I saying here? That the only reason why the silken tent and the she are being compared is that the qualities that they share are identical to each other.